Okay. Good morning, everyone. So, in a previous class, we finished the transient response of a second-order system. So, in today's class, let's solve some problems on transient response. Okay. So, I'll be taking up close to say 2 to 3 classes only for problem's sake. Okay. So, the problems are, you will find different types of problems in module 3. Okay, so let's spend about say 2 to 3 classes on problems. All right, so take the first problem. It goes like this. Okay, you can take the problem statement as I dictate the problem. A second order system is given by C of S by R of S is equal to 25 . Okay. So find its rise time, peak time, overshoot, and settling time. When subjected to unit step input. So when subjected to unit step input, US input is unit step input. All right. Also find the expression for its output response. So the last part is find expression for output response. So that is find C of t. Okay. Fine. So that's the problem statement. So let's solve it. The first one is straightforward problem. Okay. So first thing what you have to do in module 3 problems is that you need to check whether the given closed loop transfer function is belonging to the standard form or not. So if you compare the given transfer function with standard form, okay. So compare with standard form. Okay. See, this comparison is very, very important. So as we solve more and more problems, you'll be able to understand that the standard results may not be, applicable in all the cases. Okay. So if the given function is in standard form, then only it is applicable. Okay. So standard form. So first let us write the standard form or canonical form. That form is something like this: omega n square divided by s square plus 2 zeta omega ns plus omega n square. So compare the given transfer function with the standard form, right? So first of all, you need to check whether it is expressed in standard form or not. Yes, it is expressed, right? So against omega n square, you have 25, and against the denominator polynomial, you have the proper polynomial in your given transfer function. So you can apply the standard results. Okay, that is you can simply write C of t is equal to whatever 1 minus e to the power so on and so forth. So this expression holds good for this particular system. All right. Now we'll compare the denominator. Okay. Compare the denominator. Okay. So on one side you have s squared plus 6s plus 25 is equal to 0. That's your given characteristic equation. So that you are comparing with the standard characteristic equation of a second order function, s squared plus 2 zeta omega ns plus omega n squared is equal to 0. Okay. So when you compare, what you get is omega n squared, right? So against omega n squared, you have 25. So that implies natural frequency of oscillation is 5. And unit is radian per second, omega, right? So radian per second. And then you have 2 zeta omega n as your coefficient of s to the power 1. And in the given transfer function, you have coefficient of s to the power 1 as 6. Or omega n is known to you. So you can find the damping ratio zeta. So damping ratio zeta is equal to 6 divided by 2 into omega n. So 6 divided by 2 into omega n. Right. So it is 0.6. So damping ratio is 0.6. Correct. Now, by looking at the damping ratio, one can talk about the type of system. Okay, in the sense whether it is underdamped, overdamped, or critically damped. So damping ratio is less than unity. So the given system is underdamped system. Underdamped system. So this is one indication, right? So whatever C of t expression you have derived in your previous class, that is 1 minus e to the power whatever. So that was derived by considering an underdamped system. So if you get zeta greater than 1, then you cannot write this formula, correct? Because your terms will be purely exponential in nature whenever zeta value is greater than 1. So you have to be very careful while solving these problems. Okay, looks very simple, but little you have to apply the logic. Fine. So we have estimated omega n as well as the zeta value. Now you can go ahead with the calculation of time response specifications. The first being rise time. So let me write A and rise time. So rise time is derived something like this: pi minus theta divided by omega d, right? Or pi minus theta divided by omega d is omega n into under root 1 minus zeta square. Yeah. So what is theta then? So theta can be found from damping triangle. Correct. Once again, I'm repeating. Theta can be found from the damping triangle. So along hypotenuse you have 1, adjacent side you have zeta, and on the opposite side you have under root 1 minus zeta square. So theta can be written as tan inverse of under root 1 minus zeta square divided by zeta. So I've taken the tangent. Okay, tan theta I've taken. So theta, okay, you will get it as 53.13 degrees. 13 degrees. Okay, please cross check. So when you, okay, what is zeta? In the previous step, we found zeta as 0.6. So when you substitute zeta as 0.6, you will get 53.13 degrees. Okay. But remember one thing, we are not considering the linear frequency, right? We are considering the angular frequency. It is radian per second. Hence, it makes sense to convert the angle or keep the angle in radians. So you please convert this angle in radians. How do you convert? it is degree into pi divided by 180, right? So pi by 180 is the conversion factor to convert the angles from degrees to radians. So when you convert your degrees to radians, you would get theta as 0.9268 radians. Okay, 68 radians. So once you have the theta value, you can find TR. So TR is equal to pi. So pi is 3.14 minus theta 0.9268. Okay. So this is pi. So this 3.14 refers to pi. Okay. Divided by omega d, omega n into 1 under root 1 minus theta. So omega n is pi under root 1 minus 0.6 square. So find the value of TR. So you're supposed to get the rise time value. Okay, if someone has calculated, they can cross check their answer. 0.5537 seconds. So that's your rise time. First one. Rise time. Fine. Any doubts? Second part is the peak time, right? So TP. So peak time expression is similar to rise time expression except for the absence of theta term. So TP is equal to pi minus omega d or pi divided by, so pi by omega d, I'm sorry, it is omega d is omega n into under root 1 minus zeta square. So substitute TP is equal to 3.14 divided by omega n into under root 1 minus zeta square, that is 0.6 whole square. Okay. So numerator is bigger than your rise time numerator. Okay, that's because TP takes place after the rise time, right? So the time is 0.785 seconds. So that's your rise time, TP. So two things you have calculated, rise time and peak time. Now you can calculate MP. MP is also called as maximum overshoot. Okay. So let's keep this overshoot in percentage basis. Okay. Because for a physical system, the overshoot is normally referred as percentage. It is expressed in percentage basis. Now, in general terms, your overshoot is nothing but, say, for example, you consider an example of television. So, in the power specifications, voltage is your, okay, in the electrical specification, voltage is one of the parameters, right? So, normally for a television, they'll write, say, 230 volt plus or minus 20%. So, when you take 230 plus 20%, that means to say you are allowing an overshoot of 20%. That means to say above 230 volt, the voltage can go above the nominal value, that is 230 volt, by a factor of 20%. So 230 into 0.2. That's 46 plus 230. If you say at the maximum, this television may be subjected to 230 plus 46 volts, that is 276 volts. So this is the implication of overshoot in your physical systems. Okay. On the other hand, if you take minus 20%, then instead of overshoot, you will get undershoot. So basically, your overshoot and undershoot, they set up the limit of operation. So the voltage within this overshoot value or undershoot value may be regarded as the healthy voltage for the physical system under consideration. So that is the meaning of overshoot or undershoot. Okay. So let's calculate the overshoot for this particular system. So MP, okay, as I was mentioning previously, we will find out percentage MP. Okay, so percentage MP is, you can just write on the formula, e to the power minus pi zeta into 1 minus zeta square into 100, right? Percentage basis we are trying to keep it, or percentage MP is equal to e to the power minus, okay, pi is 3.14, because I have to write, because if you are not careful, you may take it as 180 degrees. You are not supposed to, because everything is expressed in radians, right? So it is 3.14 into zeta 0.6 divided by 1 minus 0.6 the whole square into 100. So percentage overshoot is 9.48%. Please check if you have got any different answers, you can share it. We'll upload the material also in the class group. Okay. So that's your MP. And then finally the settling time, TS. So settling time TS can be found as TS is equal to 4 by zeta omega. Remember one thing, this settling time we have considered by considering plus or minus 2% of steady state error. All right, 2% of steady state error. So how much will you get? TS is equal to 4 divided by zeta is 0.6 into omega n, that is 5. So it is 4 by 3. Right. 4 by 3 is 1.33. Okay. We can say that the system settles at 1.3 seconds. Okay. So that's the settling time. Okay. And then finally, you need to determine the closed loop response. Right. So for a closed loop response, you need to consider the input as well. Since the input is given as unit step function, so beforehand only we know what is closed loop response of a second order system for a unit step excitation. So C of t is equal to 1 minus e to the power minus zeta omega nt divided by the root 1 minus zeta square into sine omega dt plus theta. So what you have to do is you have to substitute zeta is equal to 0.6, omega n is equal to 5. Yeah, zeta omega n, that's all. And theta is equal to okay. You have found it in radians, right? Theta value 0.9268. 0.9268. So substitute all these values in the above relation. Okay. So upon substitution, you should be able to get the closed loop response. So just check your answer. C of t is equal to 1 minus 1.25 exponential minus 3t into sine of 4t plus theta 0.9268. So this is your closed loop response. Okay. So your closed loop response is consisting of steady state response CSS as well as the transient response. Okay. CTR of t. Together that is steady state response plus the transient response will give you C of t. So that is your closed loop response of a second order system. All right. So that's your first problem. If you are done with first problem, okay, we can take up the second one. Fine. Now the second problem you can take down. For the system shown below, obtain closed loop transfer function. Obtain closed loop transfer function. Second one, damping ratio. Third one, natural frequency. And fourth one, expression for output response for unit step input. Expression for output response for unit step excitation. All right. So we have the block diagram representation of a system. Okay, you don't have the direct description of the system. The system description is given in terms of a block diagram. Okay, fine. So this is your given problem. Let's try solving this. So first step is to find the closed loop response, right? So we need to find C of s by R of s. So that is G of s divided by 1 plus G of s into H of s. So identify G of s and H of s in your given block diagram. So this is my G of s, forward path transfer function, and this is my H of s, which is unity. All right. So substitute G of s and H of s in the standard form and try to find out C of s by R of s. So C of s by R of s, you will get it as s square plus 4s square plus 5s plus 4 plus 20, 24. So just check whether you are getting this. 20 divided by s square plus 5s plus 24. Okay, 24. So as you can clearly observe that if you were to compare it with standard form, you would have got the following standard form, right? Omega n square divided by s square plus 2 zeta omega ns plus omega n square. Now, what you need to do is the given system you need to compare with the standard function, right? So the denominator is actually agreeing with the standard form, s square, and then you have a s term, and then you have an omega n square term. So same thing you have, right? But if you look at the numerator, in the standard system, you were supposed to have omega n square. I mean, in standard system, you have omega n square. And in a given system, you were supposed to have omega n square. But omega n square is 24. So this is omega n square. This is not omega n square. This is not equal to omega n square. So directly you cannot write the expression for C of t. Of course, you can compare the denominator and you can extract the zeta, omega n value, etc., etc. But when it comes to the closed loop response C of t, you cannot use the standard formula, provided you convert this given system into the standard form. So how do I do it? So you can write, okay, since the given system is not in the standard form, let us convert the given system description into the standard form. So that can be done by, okay, you can write C of s by R of s is equal to, okay, so what I can do, I can multiply and divide with omega n square. So in our case, omega n square is 24. So what I will do, I will multiply and divide by omega n square. And this constant gain k, let me keep it along with this into, let me write 24 divided by s square plus phi s plus 24. Okay. Now you see, mathematically no harm done, right? Because this 24 is going to, cancel out with the numerator 24. Okay, but by doing this adjustment, what we have done is we have converted non-standard form into a standard form. So this is my standard form. Okay. So by doing so, you can apply, therefore, C of t becomes, okay, 20 by 24 into 1 minus, e to the power minus zeta omega n t under root 1 minus zeta square into whatever that sign term. So what you have to do is you have to just multiply the standard response with k by omega n ratio. Okay, so that's how we solve this particular problem. All right, so that is the key step over here. Okay, fine. Let us proceed with the other part of the problem. Okay, now that we have converted into standard form, you can proceed with the other part. Okay, so this itself is your part here. All right, so I forgot to mention, you are being asked to find closed loop transfer function. So this is your closed loop transfer function. Okay, I'll just highlight. This is your part B, closed loop transfer function. All right, and in part B, you need to find zeta, right? Zeta. So how will you find zeta? So 2 zeta omega n is equal to 5, right? And also in part C, you need to find natural frequency omega n, right? So omega n square is equal to 24. You can see omega n square is equal to 24, or omega n is equal to under root 24 radian per second. Okay. So omega n also been found, right? So it is under root 24 radian per second. So having known omega n value, you can find the zeta value. So 5 divided by 2 into omega n. So 5 divided by 2 into under root 24. So zeta, you will get it as just check 0.51. 0.51. So that is your zeta value. zeta. So closed loop response is found, zeta is found, omega n is found. And now finally you are left with the closed loop response. Okay. So complete the closed loop response. I will erase this part. So already you have written an expression for closed loop response. That is C of t is equal to, okay, that is part D. Let me write part D is equal to k by omega n for the given transfer function. K is 20 and omega n is 24. So 20 by 24 into 1 minus e to the power zeta omega nt divided by 1 minus zeta square into sine of omega dt plus theta. Okay, where omega d is equal to omega n into 1 minus zeta square, that is under root 24 into 1 minus 0.51 square. So omega d, you will get it as 4.206 radian per second. Okay, when you substitute, we get, you can cross check later also, 4.206 radian per second. And you need to know this theta value also, right? So theta is equal to tan inverse of under root 1 minus zeta square divided by zeta. In radians you express. So 1.035 radians you are supposed to get. So when you substitute all these values in C of t expression, you will get, therefore, C of t is equal to 20 by 24 into 1 minus, okay, I'll continue here in the second line, 1 minus, okay, just substitute e to the power, okay, minus zeta omega n, that is 0.51 into omega n, under root 24, under root 24 is 4.89 into t divided by 1 minus so you get C of t is equal to so this is the answer. Substitute, yes, substitute. This multiply, you will get it as minus 2.5 in the numerator. All right, just multiply. Try to get the values. If any discrepancy is being found, you can intimate me. You can cross check. I've checked these answers. Okay. Seems to be fine. Please confirm. All right. So that's your problem number 2. Now let us slightly raise the complexity in problem 3. Okay. So we started with a simple problem, right? And then we are trying to raise the complexity. Okay. Third. So you can take the problem statement, determine K1 and K2. So determine K1 and K2 so that MP is equal to 25% and TP is equal to 4 seconds. Assume unit step input. Assume unit step input. And the given function, the given system is something like this. This is K1 in cascade with our double integrator 1 by s square C of s R of s. And then you have this feedback path, which is not unity in this case. It is some K2 into s. Right. All right. So this is your system. And you're supposed to find what is the value of K1 and what is the value of K2. That is what you're supposed to find. Okay. So try solving this problem. Whatever it may be, you will have to start with the closed loop transform, right? So that's the first step of the solution. Right? So solve solution. What you have to do is you have to find out the closed loop transfer function first. So you take this as your h of s, and the cascaded connection, you take it as g of s. Okay. So I have g of s as the product of individual block gains and h of s as 1 plus k2s. So try finding out c of s by r of s. So c of s by r of s is equal to g of s divided by 1 plus g of s into h of s. So that is c of s by r of s is equal to g of s. So g of s is k1 divided by s square, right? K1 divided by s square as your g of s divided by 1 plus g into h. So repetition of numerator k1 by s square into 1 plus k2s. Okay. So try simplifying this and check whether you get c of s by r of s as something like this: k1 in the numerator divided by s square plus k1 k2 yes plus k1. Right. So this is your transfer function. Now compare this transfer function with the standard form. C of s by r of s is equal to omega n square s square 2 zeta omega ns plus omega n square. All right. When you compare, what do you get? First, you check whether the given system description is in standard form or not. Yes, it is in standard form, right? Because you have omega n square term here as well as here. So omega n square term is appearing both in the numerator as well as in the denominator. So by comparing, we get omega n square as k1, right? Omega n square as k1. And we want to find what is k1 and k2. That's the reason I keep k1 as omega n square itself. All right. And then we have 2 zeta omega n is equal to product k1 into k2. So probably that will give me k2 value. So k2 is equal to 2 zeta omega n divided by k1. So if you can find out k1, you can find k2 provided zeta and omega n values are given. Okay. So how do you find these zeta values? Okay. So if you can recall, I had already mentioned your maximum overshoot. Maximum overshoot MP is a factor of zeta alone, right? So you have maximum overshoot specification. So when you solve this overshoot for zeta, you will get the value of zeta. So probably you can use MP relation to find zeta. Once zeta is known, you can find, if I'm not wrong, omega n. So having known zeta will enable you to find out omega n. Let's see. So first let us take up MP. So MP is given as 25%, that is 0.25, which is equal to e to the power minus pi zeta divided by under root 1 minus zeta square. Okay, so on LHS you have MP value which is 0.25, and on RHS you have the relation for MP. So probably what you can do is you can take out the natural logarithm on both sides. So on LHS it becomes ln of 0.25, which is equal to negative pi zeta divided by under root 1 minus zeta square. So ln of 0.25 basically gives just check, ln 0.25 is negative 1.3863 minus 1.3862. Okay. So this negative sign gets absorbed, and if you substitute pi as 3.14, and if you carry out further simplification, okay, further simplification, you can write something like zeta is equal to under root 1 minus zeta square. I'm substituting pi as 3.18 there. Okay, so you get 0.4412. Okay, and then squaring both sides. Squaring both sides. So I get zeta square on LHS. Similarly, under root gets vanished. So I have 1 minus zeta square here. And then I have square of 4412. Okay. And when you take this side and when you solve, you basically get zeta square as, okay, you simplify. So you get zeta square as 0.1947 divided by 1 plus 0.1947. So that implies zeta is equal to under root of this. This is the value you get, zeta. Right. So zeta is 0.4037. Okay. Once you have zeta value, you can proceed with TP. TP is given as 4 seconds, and TP is pi by omega n into under root 1 minus zeta square. So zeta is 0.4037. Solve this. You should get omega n as 0.8584. 8584 radian per second. So that's your natural frequency of oscillation. Yeah. Once you find omega n, you can find K1. So K1 is simply the square of omega n, that is omega n square. So K1 is equal to 0.8584 whole square, right? So when you square omega n, you will get the K1 value, and K1 value you will get it as 0.737. So that's your K1, 0.737. Once you have K1, you can find K2. So K2 is 2 into zeta is 0.4037. Okay, it's okay. Let me write once again. K2 is 2 into 0.4037 into omega n, 0.8584 divided by K1, 0.737. So that will give you K2 value. So K2, please check, 0.94. So that's how we find the K1 value and K2 value. Okay, so that's your problem number 3. Okay. Are you following? If you are not following, please let me know. Okay, if you are not following, please let me know. Okay, that's problem number 3. Now let us take the 4th problem. Fourth problem. Yeah. Please take down. It says a system is given by differential equation. A system is given by a differential equation. Okay, so this is a given differential equation where y is equal to output and x is equal to input. Determine all time domain specifications for unit step input. So determine time domain specs. TD is time domain. Determine all the time domain specifications. Okay. So as you can see that, in every question is different from the other, right? So in the fourth question, you do not have the system description in the form of a block diagram or the standard form, that is C by R. So you have been given with differential equation. So from the differential equation, you need to determine the transfer function. Okay, so to determine the transfer function, what we need is output by input ratio, right? So Laplace transformation of output to the Laplace transformation of input under zero initial conditions gives the transfer function. So with respect to the given problem, the output, they are asking us to take it as y, that is y of s, and input we are supposed to consider it as x. So if we can take out y of s by x of s ratio, we will get our closed loop transfer function. Fine. So what you can do is convert differential equation into Laplace domain. So that is differential equation which is expressed in time domain into Laplace domain. So you have double time derivative, hence s squared plus 4, s square into the variable y of s plus 4s into y of s plus 8 into y of s is equal to 8 into x of s. So take y of s as common so that you get a second order equation, which is s square plus 4s plus 8 is equal to 8 into x of s. And then you take out the ratio y of s by x of s. So you will get 8 divided by s square plus 4s plus 8, right? So that's your given transfer function. And you can see omega n square is present in the numerator as well as it is present in the denominator. So as a comment you can write it is in standard form. It is in standard form. So once you find that the given transfer function is in standard form, you can directly apply the time domain results, okay, as in TR, TP, and even you can directly write C of t expression. Okay, so just compare it with standard form. So compare the system denominator with s square plus 2 zeta omega ns plus omega n square is equal to 0. So you will get omega n square is equal to 8. That implies omega n is equal to under root 8. That is 2.83 radian per second. Okay. So that's your omega n, 2.83 radian per second. Once you have omega n, you can find zeta. So 2 zeta omega n is equal to 4. So that should give you the zeta value. Okay, I will leave it to you. Zeta value is 0.7067. Zeta value. Okay. So you know omega n and you know zeta. So you can find out the time domain specifications. Okay. You can find out the time domain specifications. TR is pi minus theta divided by omega n into 1 minus zeta square. TP pi by omega n into 1 minus zeta square. Yes. 4 by zeta omega n. And percentage MP. Okay, that's the fourth specification, right? Percentage MP is minus pi zeta under root 1 minus zeta square, the exponential term into 100 into 100. Okay. So it's a straightforward substitution. Okay. Theta you need to determine, that is there. So check thesis theta, where theta is pi by 4 radians you are supposed to get. Okay. Pi by 4 is 3.14 divided by 4. That's your theta. Okay, so you find out all time domain specifications, and in the end, you can find out C of t. C of t is equal to 1 minus the conventional formula. Okay, this formula. So just solve this.